Hey, pre-calculus students. It's time for lesson 651. I think it is. We got some linear programming and optimization. And if you were with me for Algebra 2, you already did a little bit of this. I'm going to borrow some stuff that we did a couple of years ago and get us all warmed up for today's lesson. So I've already passed on some notes for you, and so all the blanks are filled in and all that, but I just want to talk you through how I got to all that stuff, so that you can do the same thing when you do your homework. So there'll be some calculator stuff coming up here, but you just more or less want to follow along with the notes and maybe have out some different colors or highlighters or something so that you can follow along with me as I'm talking through these problems. So first we'll define this here. Linear programming is a mathematical technique that allows you to make optimal decisions from a complex set of choices, otherwise known as optimization. Most profit, less loss, things like that. How to get the most out of something, which is what we're all about. There's going to be a set of constraints. There's going to be some things like, hey, you can't have negatives. You're selling stuff. You only have so much room. You're going to have like how much each thing costs, and production costs and whatnot, and then how much people are willing to pay for these things. So we're eventually going to look for either a maximum value or a minimum value of something called an objective function. The objective function is oftentimes like the profit function. It tells you that if I sell this many of these and that many of those, this is how much money I'm going to make in the long run. I want to look for the optimal number of products to sell of each kind to make me the most profit overall. So you can see that in your handout. Find a maximum or a minimum value of an objective function subject to certain constraints. Now, those constraints are given, at least in this lesson, as linear equations or inequalities, less than equal to, greater than equal to. In the graph, once you're done, you'll have a picture that shows you your answer. And there will be a shaded region that's known as the feasibility region. That's where you're going to make some money. All possible solutions of the two things that you're trying to sell will be in the shaded area. We got your X and your Y vertices. When you want to find the very, very best solution, a key area to focus on will be at the corners, or I should say at the vertices of the feasibility region. So you're going to need to find those and then evaluate them in your objective function. So you've got there an example below, but I've already worked that one all up. So I've done the same thing over yonder on this paper here, but I'm going to color code it, okay? It's going to be the exact same problem, but I've color coded it so that you can see what you might do as you are working stuff out. So here we go. We got a garden center that grows only junipers and azaleas in a greenhouse that holds up to 3,000 shrubs. Now I've already highlighted some stuff in the first center. I've got two variables. Mr. Edmondson is mowing today. He's not going to mow the junipers or the azaleas. But I got two things, and I'm going to have to pick which one is going to be in the x-axis and which thing's going to be in the y-axis. And you can already see that in your notes. But we've also have this thing about holding up to 3,000 shrubs, so that's like a less than or equal to type of situation. You can see in your notes I've already turned that into an equation. X and y is less than or equal to 3,000. But that's where I get that information, is words like up to. And then it says due to labor costs, so here's another constraint. The number of azaleas grown must be less than or equal to 1,200 plus 3 times the number of junipers. Okay, so there's another thing that I'm going to have to turn into an equation in order to get a line, and then I have to know whether it wants to shade above or below that line. Azaleas were y, and junipers are X, so we would have another equation there. Market demand for azaleas is at least twice the of juniper, so there's another constraint that needs to be turned into an equation. And then we have that the center makes, and then this is our objective function, makes a profit of $2 per juniper, $1.50 per azalea. So you basically have to start with one sentence at a time and say, how do I turn that into an equation? Once you've picked out what your variables are going to be, junipers and azaleas, X's and Y's, then you have to write inequalities for those things. And then we'll go ahead and get to the graphing. So that objective function is going to sit there for a while and just look pretty until we're ready to analyze it, until we have some XY points to plug in and see what kind of profit that gives us. This is the way we draw this one. I got junipers as X, azaleas as Y, and profit, the P function, or F of X and Y, or P of X of Y, is 2X plus 1.5Y. Okay, so I need some XYs first. And the object is to optimize your profits, obviously. So here we go. From the yellow up above there, junipers and azaleas, up to 3,000 shrubs. We're going to turn that into X plus Y is less than or equal to 3,000. The second sentence, the number of azaleas grown must be less than or equal to 1,200 plus 3 times the number of junipers, would turn out to be like this. Y is less than or equal to 1,200 plus 3x. The next sentence in blue, market demands for azaleas is at least twice that of junipers. Y is greater than or equal to 2x. And then lastly, we already have our objective function that would be there in orange. So we've got these three, but we also have a couple of other things that are true as well. And that is that we're not going to allow for anything less than selling 0 junipers or 0 azaleas. So we are going to use all positive values, or 0, which would be unfortunate, but it might happen. Common sense says that we have these two equations as well. Those will be the axes. The X and Y axes are also boundaries. We cannot have negative bushes or negative flower. All right, so on the second page of your handout, all those functions got copied over. There's the objective function, the linear equations and inequalities. You've got your constraints, and then the key concepts for linear programming there. We need to graph the region corresponding to the solution of the system of constraints, find the coordinates of the vertices of the region formed, and evaluate the objective function given our XY points that the rule says that's where you're going to find the minimums and the maximums, is at the vertices of that region. Righto. So that's exactly what we did. I'm going to get the calculator up here in a second and kind of show you the buttons that I pushed to get to where this would make sense. All right, I already got 2 of the 3 equations set up here. Remember, if you want to go and change those equal signs to inequalities, you're going to arrow over so that the cursor is a big one around the whole thing, and you can change your styles for these things here. If that's not on, go to your apps and turn off or on number 7 in equalize. That's where it gives us those things. All right, back to this. I've got my last one here that I'm going to type in, and that one is y is greater than or equal to 2x. I'm not going to do the ones with the axes. That's kind of silly. I'm just going to change my window to make everything fit. So right now, let's see. I don't even know what my window is at. It's not a good window because I've got like up to 3,000s of somethings. So that's going to be pretty anticlimactic there, how it just shades everything. So this is a really bad window to use. So I'm going to put on my thinking cap here and realize that I don't want anything negative, and then I need to give myself space for up to 3,000 of each kind of plant. So I'm going to change that to 0 to 3,000 to make these like, I don't know, every 30 or something like that. Might make sense. Same thing here, go from 0 to 3,000 and by 30s is probably a good scale. That's much better. So now when I go in and graph it, I'll have the x and the y axes in the bottom, along the left and on the bottom. And then it'll do the graphing here for the stuff that's really important. Uh-oh. What kind of scale did I do here? It was a little clunky. I think I may pause and see I did something wrong here in my window. No, it wants to just... oh, 30. Yeah, that's bad. Go down here and pick 300. Up 1. Up 1. 300. Alright. Fewer lines to draw in here now. Ah, snap. That one's wrong, though. I did it twice, didn't I? You could watch me make my mistakes. 300. Graph. Right. This will be faster now. User malfunction, right? Okay, there's our 1, 2, 3 functions, and the area that we're concerned about is where all the shading is. I want to show you how you can get it to just shade that on a calculator, and that would be this new thing. You go to second calculator, and if you get the most updated operating system, it has inequality. So you can arrow over to this, and it's got points of interest trace, inequality intersection, or union. We want the intersection of all the shaded regions, so I'm going to choose 2, and I want you to watch what happens here. It's going to shade that stuff in first with some big dots, and then on the next one, anything that's not an overlap, it's going to erase. And here comes the last one. Anything that doesn't fit in the overlapping of the shading is going to get erased. And we are left with our feasibility region, and we care about this corner, this corner, this corner, and this corner. And how we can kind of take a look at some of those is, again, over to the inequality thing and pick number 1, points of interest. And it'll put the cursor right there, and there's one of our options for a possible best answer. So I'm gonna just list these XY points that are on the edges of the picture. So 450, 2550 is an option. We also have the origin down there as an option, but we know that's going to give us a minimum value. And then I think we can arrow around a little bit. There we go. That one right there, it says it's at 1,000, 2,000, and we have the last one that's right here. I'm going to get to that by going trace on the red line and asking it for the 0 point. And it'll give me 0, 1,200. So there are the 4 that we need to plug into our objective function. And you can see that my graph looks like that graph. I've labeled it with junipers on this side and azaleas over here. And I've got my 4 main points in there. So once I got those 4 points, then I do something like this. I got my objective function, function xy. This is my profit function, right? So I plug in each of those coordinates, 0, 0, 0, 1,200, 1,000, 2,000, and 450, 2550. You can take guesses what do you think might be the best, but you won't really know unless you plug them in. So you go 2 times 0 plus 1.5 times 0 is 0. That's our minimum. The second one gives us $1,800 of profit. The third one gives us 5,000, and then you check the last one, it's 47.25. So this one right here at 1,000, 2,000 gives us a maximum value. So there's our maximum right there. That is the thing that we'd be shooting for in terms of the 2 types of plants that we would want to sell. So that's how they work. That's one of the examples that they actually gave in the book. And you just got to fiddle around with your window so that it fits. Use your inequalities and shadings, and then remember that extra little thing on the calculator, the inequality thing, where it will shade just the part that overlaps. That's really what you want. Pull out those vertices, and that's what you're going to analyze. Trick is mostly turning the sentences into equations, but you people are smart and good looking, so I think you can figure it out. All right, you got your assignment there in front of you. You should probably do that before it's due. Talk to you later.